Here's my tracker program. As you can see, the weight is making an elliptical motion. The graph on the side proves this, and as you can see, at first it starts off very elongated, but then becomes more and more circulated, and then becomes elongated once again. This shows how its course changes over time and how its shape may vary depending on how it's dropped. I believe if the weight continued oscillating, it would recycle through the ellipses in, hypothetically, the same places and repeatedly. One of the most crucial equations for the fourth lab is figuring out t, the period of oscillation, but that one's very simple. So the more complex way of doing it is t equals 4 pi squared times the square root of m divided by k, m being the mass of the object in oscillation and k being the stiffness of the spring. But since t is very easy to find and k is what we were really trying to solve, we switch them around. And the new equation is k equals 4 pi squared, sorry about the typo, that's supposed to be 2 stars, times the mass divided by t being the period of oscillation. So now once I find my inputs, being the mass of the object being 0.402 kilograms in scientific notation, t simply being the time it takes for the top peak of the oscillation to go to the next peak of oscillation, or the lowest point of the oscillation to the next lowest point of the oscillation. And for this one is 1.71 seconds. So once you divide 0.402 kilograms by 1.71 seconds, then multiply it by 4 pi squared to the second 4 pi squared, you get k, the spring stiffness, being 6.9104. I believe this will vary because different students will have different feedback from tracker because of human error, so this is what I got. The next crucial equation is trying to figure out the spring's relaxed length. For this one, we need to figure out the spring's equilibrium, but that was already given by the video lecture, the first lesson of row physics, and that being the length of the spring in equilibrium with weight at the end. With 0.402 kilograms in the spring and its spring stiffness being k, being 6.9104, the spring's length in equilibrium is 0.7 meters. Now the equation to figure out the relaxed length is we're trying to solve for LO, being relaxed length of the spring. The equation is LO, relaxed length of the spring, is equal to the length of the spring in equilibrium minus the mass of the object times the gravitational force divided by k, the spring stiffness. After inputting my variables being 0.7 meters for the spring length, the mass of the object, the gravitational force being 9.8 meters per second, divided by the k, the spring stiffness, we get the result of being 1.2990, or being the scientific length. We get the result to be LO is equal to 1.2999 meters. Here's my Python program. The first thing I had to change in it is change the ball's mass, being 0.402 kilograms. Then change the ball's starting position and several other things. But the most important thing that I had to change was the total force acting on the system, being the force of gravity, the spring's force, F net, the ball's velocity using Newton's second law, and the ball's position. Several other things I needed to change was how to calculate the energy changes. A few of the other things I needed to change was the spring's update and also the calculation of how much energy there is in the system. After that, I input my data received from tracker and ran in my module, and here are the results. And here's my Python program. As you can see, the ball is making elliptical motion and begins a very straight path at the beginning, as in the video. The blue line is the kinetic energy line, the red line is the gravitational potential energy, the green line is the spring potential energy, and the yellow line is the total energy, or F net. As you can see, the yellow line doesn't bend or curve in any way. I believe this is caused by both the gravitational potential energy and the spring potential energy canceling it out, therefore it remains straight.